So once we've entered those two lists, we're going to go back and push Stat and move over to the test menu and scroll down and find the chi-square goodness of fit test. And then the setup for the test is in figure 11.2.1 below. And again, next to this DF that stands for degrees of freedom, which once upon a time we had to worry a lot about when we had to look up values in tables, which we no longer do. But next to degrees of freedom, you need to put a 5. Since we have 6 categories, okay, the 6 sides of the die, and the number of categories minus 1 then is 5. Okay, so next to degrees of freedom, this is not always a 5, but in this case it's because we have 6 categories and 1 less than 6 is 5. Alright, so again, the default on this for observed and expected are L1 and L2. If you put your data someplace else, you need to put those list names here. But once you press enter on calculate, you will see the results in figure 11.2.2. So again, the only things on this output screen that we are interested in is the chi-squared test statistic and the p-value. Again, degrees of freedom. It's important to get the right one on the input screen, but we're not going to use this one in the output screen for anything. And again, these contributions, again, goes beyond the level of this course. We're not going to discuss those values either. But StatCrunch is a different story on what gets entered here, especially on this weird case of a die because we are expecting an equal number in all categories. Okay, most qualitative survey questions that we give, we do not expect an equal number in all of the categories for those particular questions. So in this case, we would either open the data in StatCrunch or we would need to enter it. So again, we would enter in one column our observed counts. But in this case, we would expect an equal number in each category. So in this case, we only need to enter a list of observed frequencies. Okay, this is not going to be the case in any of the homework problems because we're going to expect, more, blue M&Ms than brown ones, for example, or whatever it is that we're looking at data for. But in this case, for fair die, we are expecting an equal number in each category. So now we're going to choose Stat, Goodness of Fit, chi-square test, and we're going to make our input box look like the one below. So we would choose where we put, so this observed is the name of that column. But then under expected, we would bubble in the dot next to all cells in equal proportion. And that's because the null hypothesis says that we have a fair die. And if HO is true, then we would expect an equal proportion for all sides of the die. Alright, so since this problem involves testing whether or not we had a fair die, we will check the box all cells in equal proportion. But again, however, in almost every data problem, this will not be the case. There's a few cases where we're going to want to test if something has kind of like a uniform distribution across all the categories or something, but it's rare. So we will see what to do in the case where we do not expect an equal proportion in all categories in the next example. Okay, so once you've entered that, you can hit compute, and then we get this output table in StatCrunch. So again, the numbers that we're interested in here are our chi-square value and our p-value. And here, again, I hate that everything is capitalized in the starting on these cells, which for most things is no big deal, but this is not cap n. This is actually lowercase n. But then you'll see it has the observed counts that we had entered, but then StatCrunch computed these for us. So StatCrunch computed the expected frequencies for us. We did not enter those in a list in a column to begin with. Now on the calculator, we did have to enter that list of values in there, but StatCrunch computed it for us when we told it we expected an equal proportion on all categories. It took this 500 and divided by the 6 categories we had to get those numbers, just like we did in the problem where we did it with the calculator. But again, no matter which technology we use, we're going to get the same value for chi-square. Both of them are using the same formula. So again, if we just set a couple of these up just to see what it's doing. Again, it's going to take what we observed in that first category minus what we expected, which I'm just going to write that as 506, and square it. And then it's going to divide by what we expected in that cell. And we would do that for each of those 6 individual cells down to this last cell where we would get 87. Let's move that over. I'm not going to be able to fit that in there. 87 minus, again, what we expected in that cell, 506, and square that quantity. And again, dividing by what we expected in that cell, which was 506. So again, a lot of key punching if we had to do it, but we don't. We're just going to cheat, and we're going to look at on our output screen where it says our chi-square value there is about, if we round off to 2 decimal places, about 1.50. Again, keeping in mind that this 1.50 does not measure standard deviations away from a claim. So again, we have to rely on the p-value here to tell us if we have something really unusual or not so unusual that just happened, assuming HO is true. So on that same output screen, we'll get a p-value of 0.9126. So again, doesn't matter if we get that from the calculator or from StatCrunch, they're the same. Again, that is always an area and a right tail. And now here, I just drew this for more perspective because, you know, the total area under the curve is 1, and so we're at 0.9, which means we've got practically the whole thing shaded. So again, axis here starts at 0, runs off to infinity. The particular value that we got for our test statistic was 1.5. So again, that is the cut score between the unshaded and shaded region. And again, these are always right-tailed tests. So we would shade to the right of 1.5, and again, that shaded area there is 0.9126. So again, we compare that to our value of alpha, and it's either less than or equal to or greater than. In this case, our alpha value was 0.05. Okay, 0.9126 is way bigger than 0.05, so in this case, we would fail to reject. So since the p-value is greater than 0.05, we will fail to reject HO. So again, if we fail to reject, that means there is not significant evidence to conclude, and then we just go back and we grab the wording from HA. So there's not significant evidence to conclude and so it read that the observed frequencies are inconsistent with that of a fair die. Or if we take what we had written parenthetically after that, we could also just say there is not significant evidence that the die is unfair. So again, we haven't proved that the die is fair. Okay, we're just saying that we didn't have enough evidence to show it's unfair. So again, same thing as back in the last chapter with, you know, the not guilty verdict versus innocent. So we didn't prove somebody innocent, we just didn't find enough evidence to find them guilty. Okay, so kind of the same thing here. We just didn't find enough evidence to show that the die was guilty of being unfair. Okay, but we haven't proved the die is a fair die. All right, so it's a couple just follow-up questions for concept pieces here. So based on your hypothesis above, why do we think the observed and expected values differ? So remember, every time we take sample data, it almost always is different from what we think it's going to be under the claim in the null hypothesis. And those differences happen for one of two reasons. Either we just think they're random sample fluctuations, or we think the differences are evidence that HO is in fact a lie, which is why then we reject it, and we conclude HA instead. So in this case, if we go back, we failed to reject HO, which means that we think the differences between the observed and expected frequencies are small enough to be just due to random sample fluctuations. Otherwise known as sampling error. So although we didn't get exactly the same count in all 6 categories, we're like, they're close enough that we don't think that we have evidence that the die is unfair. We just think that those differences are just due to random chance sample fluctuations that happens when we collect data. But again, we have to keep in mind when we do these hypothesis tests, they are based on sample data, so we may have concluded incorrectly. So we concluded correctly based on what we saw as evidence, but that final conclusion might be incorrect with respect to an entire population. So what type of error may have been made in our decision above? So again, in here we failed to reject, so we run the risk of failing to reject a false null hypothesis, which would be a type 2 error. Okay, so on any hypothesis test where we fail to reject, we run a risk of a type 2 error. On any hypothesis test where we reject HO, we run a risk of a type 1 error. And if ever asked, did we make those errors, the right answer is, we don't know. Okay? So at the end of the day, we make a decision the best we can based on the evidence we've seen. But just like in a jury trial, after they come back with a verdict, they're never ever going to be 100% certain that what they just said was actually correct.